Okay. Well, hello everybody and welcome to Sage Live March 2023. My name is Gauri Srinivasan. I will be your Master of Ceremonies for today. A little bit about me. I am currently the Deputy Division Leader for Physics Division at Los Alamos National Lab. I have a PhD from the University of New Mexico in Applied Mathematics. I joined LANL as a graduate student in 2005, and I've been at Los Alamos ever since. And I became a staff member in 2011. My research interests include uncertainty quantification, data analysis, machine learning, and I've led projects in all of these areas. While I'm not busy at work, I love living among nature in New Mexico, and you can find me hiking on the trails with my dog, and I love bird watching as well. So welcome again. Now, before introducing our speakers for today, let me briefly explain what the SAGE journey is all about and how SAGE Live fits into that journey. SAGE Journey is a program whose mission is to inspire and encourage students to explore STEM careers for their future. We do this by offering free summer camps, paid internships, professional growth sessions, and many opportunities to connect with professionals. SAGE Live is a part of the SAGE Journey. It is a monthly online gathering of students. The topics covered are relevant to your journey, whether it is career-related, such as designing your life, resume workshop, or how to prepare for an interview, or new and exciting topics such as quantum computing, AI, and machine learning. Today, we have 3 guest speakers from 3 different national labs, and they will share a little bit of their career path and their current job at the labs. Please feel free to join the conversation by asking questions in the chat or unmuting yourself to speak. Let me present our first speaker today, Kathy McCarthy. Welcome, Kathy. Kathy McCarthy is the director of the US ITER project at the Oak Ridge National Lab. She joined the lab after 3 years as vice president for science and technology and laboratory director for the Canadian Nuclear Laboratories. She previously held a variety of engineering and leadership roles at Idaho National Laboratory, including director of domestic programs in INL's Nuclear Science and Technology Directorate, director of the Light Water Reactor Sustainability Program Technical Integration Office, and National Technical Director for the Systems Analysis Campaign for DOE Office of Nuclear Energy's Fuel Cycle R&D program. McCarthy began her career in fusion technology with a focus on liquid metal blanket designs. She earned her PhD in nuclear engineering from the University of California, Los Angeles, with a major in fusion engineering and minor fields of nuclear science and engineering and physics. She was inducted into the National Academy of Engineering in 2019 and has received 2 American Nuclear Society presidential citations, and her awards include the 2022 Fusion Power Associates Leadership Award, 1996 ITER US Home Team Leadership Award, and the 1994 David Rose Award for Excellence in Fusion Engineering. McCarthy has served on the Fusion Engineering Energy Sciences Advisory Committee from 1999 to 2013 and has held numerous ANS leadership positions. She was elected as a fellow of the American Nuclear Society in 2021. She enjoys traveling, spending time with her family, and cheering on the University of Arizona Wildcats. Thank you so much, Kathy, for being here today.
Thank you so much. Let me get my screen shared and I will tell you a little bit more about what I've done and how I got there. All right, let me make sure now. I think it's pulling up. Can everybody see the slides? Perfect. Yes. All right. So the promise and power of fusion energy. There is a lot going on right now, and I'm very excited to be a part of it. I want to start out by telling you how I got to where I am. I am the granddaughter of immigrants. My mother's parents came from Spain. My parents met at UC Berkeley. They were both in school at the time. I lived in Livermore for many years. My parents both worked at Livermore Lab and until we moved to Arizona. My plan was to major in music. So that's a picture of me. I was in the band. I played clarinet and saxophone, but really, really enjoy music. I still enjoy music, but I made a last minute decision to switch to nuclear engineering. I had a teacher in high school, Malcolm Wells, there he is, who talked to us quite a bit about nuclear energy. And my senior year in high school was when the 3 Mile Island accident happened. That was an accident, a nuclear plant in the United States. So I learned quite a bit about it. And I thought, that sounds interesting. So I decided to go to University of Arizona, which at the time had one of the leading nuclear engineering programs. So you see up at the top, it says Bear Down, Arizona. I won't tell you the story behind that, but you might want to Google it. It's actually a pretty interesting story at where it came from, but I am a big University of Arizona fan. My training there as a nuclear engineer was really prepared me for my career. And one of the people that kind of took me under his wing is Norman Hilberry. That is a picture of Norman Hilberry. He is in the nuclear world one of the people involved in the very, very early days. And so he was just instrumental in helping me to get interested in nuclear engineering. Now, it didn't occur to me when I went down to University of Arizona that it would be kind of unusual to be a female in nuclear engineering. But when I walked into my physics class, it was actually very clear. So one of the things that I did is I joined a sorority, and that sort of helped me balance things all day. I was mostly around men. In the evenings, I was mostly around women. So on average, it actually worked out very, very well. Then I went to graduate school, and I chose University of California, Los Angeles. And at the time, they also had a strong nuclear engineering program. And I started out, I was going to study fission energy. Fission, those are the plants that are now providing about 20% of US electricity, but more than half of our carbon-free electricity. But I got interested in fusion, and there were a lot of reasons for that. Fusion is by its very nature very international, has some very challenging problems to solve, did back then, and actually still does. And my advisor, Mohammed Abdu, I was very lucky because he introduced me to people from all over the world very early in my career, and people who ended up in very prominent positions. And one of the things I would really advise all of you as you're trying to decide what to do, get to know people who are doing things that you're interested in, because they can be just a huge help in your career. So finished my PhD, as you heard earlier, working on liquid metal blankets. And I had an opportunity to go to West Germany. This is before reunification, just before reunification. So I spent 6 months at what was then the Kernforschungszentrum Karlsruhe, because they had experimental work. I did modeling for my PhD. I did not do my own experiments, but I relied on experiments that others did. They had a lot of experiments going on there, so I had this opportunity to work in Germany, in West Germany, for 6 months. And then I had an opportunity for an even bigger adventure. I was asked if I was interested in participating in what was called the Department of Energy USSR Young Scientist Program. And I did this from 1989 to 90. I was there for a year. And I have to tell you, it was for us, as my husband and I, because my husband and I went to Germany together. I got married in graduate school. But as we took a ferry from Stockholm into what was then Leningrad, now called St. Petersburg, and as our ferry with our old Volvo station wagon we bought in Germany was pulling into the port in Leningrad, and we saw the Cyrillic letters, and I thought, oh my gosh, what in the world am I doing? But I can tell you, it turned out to be just an amazing experience that I still benefit from. I left the Soviet Union in August of 1990. In December was the coup, so I was the first and last person to ever be in this program because the Soviet Union no longer existed. So the majority of my career has been at the Idaho National Laboratory, and I started out in the fusion safety program. This picture here is a bird's eye view of one of the areas where there are nuclear reactors. And I think somebody might need.
Now you're muted, Kathy.
Okay, am I back? Can you hear me? Okay,
yes, we can.
Thanks, Verena. So I had the opportunity at Idaho National Laboratory to spend about half my time in fusion and half my time in fission energy. And so I started with the fusion safety program and then worked on Gen 4 Generation 4 nuclear energy systems. These are the next generation of reactors. And as you heard earlier, the Light Water Reactor Sustainability Program, which is developing technologies for the current fleet. I then had an opportunity, it's time for another adventure, to go to the Canadian Nuclear Laboratories. And this, for those of you that don't know where it is, it's north of Buffalo, New York. It is just as cold and snowy as you see there on the right-hand side. A lot of really exciting work going on up there. But then I got a phone call and an offer that I couldn't resist. There is an experiment being built in southern France, and you can see it on the right-hand side. This is a bird's eye view of it. A fusion experiment, multinational, that I'll talk a little bit more about. But I had worked on the ITER project very early in my career back in the 90s when it was in the design phase. So this was an opportunity to lead the US contributions to the experiment. And so that's how I ended up here in Tennessee. I never would have expected when I was in graduate school or undergraduate or even in high school that this is where I would end up being. But I had a lot of amazing opportunities. And another little piece of advice, take advantage of adventures when they're offered to you. They're definitely worth it. All right, so let's talk specifically about fusion, because that's what we're gonna be hearing about today. So is it science fiction? I'm curious how many of you have heard about fusion in Star Trek? And did you know that you see in the upper left-hand corner, DOE reactor plans were used as a movie prop in Iron Man? Also, in Back to the Future, Doc Brown's compact Mr. Fusion reactor, that's what you see right there. So fusion has been in the movies sort of as something of the future, but where are we now? Well, first of all, the sun is a great big fusion reactor. And fusion is the process that powers the sun and the stars. It releases energy that makes life on Earth possible. So we can create a hot plasma and fuse hydrogen atoms. That's what's happening on the sun and on other stars. We can use that. We can convert it into electricity. So basically, what we're trying to do is bring a star to Earth, and that is just about as challenging as it sounds. So let's talk first about the fusion reaction. There are several different isotopes that you can get to fuse, and the energy required to do that depends on the specific ones we're talking about. One of the easier ones, not easy, but easier reactions to make happen is with two isotopes of hydrogen, deuterium and tritium. So the temperature at the center of the sun is about 15 million degrees centigrade. And the sun is very, very large and has very high gravity. And that's what pushes everything together and gets the reaction to happen. Well, we don't have quite those pressures here, except in inertial fusion. You'll hear about that in a second. But in some cases, what we actually have to do is go hotter than the temperature at the center of the sun. So our goal with what we call magnetic confinement fusion, and that's where we confine this plasma, which is charged particles. You can confine it with a magnetic bottle, basically. You only have to get to about 10 times hotter than the center of the sun. Challenging, yes. Now in inertial fusion, there's very, very high pressure and high temperatures, but high pressure for a short period of time. I'm going to focus a bit more as I talk on the magnetic fusion side, because you're going to hear the next couple of speakers talking about inertial fusion. But the goal here is to get this fusion reaction to happen. It produces an alpha particle, it's a helium nucleus, and a fast neutron, 14 MeV neutron. And you can think about that as something that's going to come out and punch holes in materials. So you can see that one of the big challenges with fusion is developing materials that can withstand those neutrons. But fusion can deliver abundant, carbon-free, safe baseload power at large scale, possibly at small scale too. People are trying to work on that. So there's a lot of reasons why those of us that work in the fusion community are so excited about what we're working on. So fusion actually is real. It's not just science fiction. It was first demonstrated for seconds in what we call tokamaks in the 1990s. A tokamak looks like a donut. And there are many different permutations of this basic donut shape that are being looked at. But the early tests, first was in the United States at Princeton Plasma Physics Laboratory at the Tokamak Fusion Test Reactor, where they produced 10 megawatts of fusion power. They had to put more energy in than they got out of it, And obviously, ultimately, you have to get more energy out than you put in. But it was the first time that that much fusion power was produced in a controlled experiment. Then in 1997, the Joint European Torus in the United Kingdom produced 16 megawatts of fusion power. And most recently, at the Joint European Torus in 2021, 59 megajoules of sustained fusion energy was created for about 5 seconds. And as I said earlier, these are tokamaks. Now, fusion ignition, which in the fusion world is one of the big goals in order to get to practical usable fusion energy, fusion ignition, where you have more energy out than what goes into the target, was demonstrated in 2022, just in December of last year at Lawrence Livermore National Laboratory. And our next two speakers are going to talk a little bit more about that. That approach is that inertial confinement, where they're squishing the fuel together to get the reaction to happen. But there are many other approaches to fusion that are under consideration. And that's really good because we're not sure which is going to turn out to be the best. There are different shapes, there are different sizes, there are different approaches. So many, many things that are being looked at, and the private sector is investing about $5 billion in the development of fusion energy. And the government is investing on the order of $1 billion per year. So a lot of excitement around this, a lot of work that needs to be done. Now I'm going to take my last few minutes to talk to you specifically about the project that I am a part of, and I'm responsible for the US deliveries to the ITER project. It is a multinational collaboration. 36 different countries are involved, 7 what we call domestic agencies. And the goal is to demonstrate the scientific and technical feasibility of fusion energy. And it is a large experiment. This is the bird's eye view of the ITER site. You can see the map on the upper left where that red dot is. It's located in southern France outside of Marseille. Not a bad place to have to travel to, I will admit to you. It is a tokamak, and what you see in the upper right-hand corner is the tokamak itself. The arrow points into the tokamak assembly building where things are being assembled. So this is looking down onto the tokamak assembly building, and on the left-hand side, you see the tokamak pit. That's where the tokamak is being assembled. Over on the right-hand side is where they put all the different pieces together. Here's an example of one of what was considered the most challenging engineering lift of the project. This is the base of what they call the cryostat. The cryostat creates this is the bottom of it. It also has sides and a top, but it creates a very cold bottle, important for superconducting magnets.
Kathy,
yes.
We have a question here. Why is it called a tokamak?
Tokamak is a Russian. It's a Russian word. So the concept was invented by the Russians, and the Russian word for it is tokamak. So that's the origin of it.
And then another student asked, what materials did they use for containing the reactions?
So what's really important here, and I talked about a magnetic bottle, because we're 10 times hotter than the center of the sun, there is no material that can touch that and not get melted. So you use, in the case of magnetic confinement, this bottle that keeps a distance between the very, very hot plasma and the materials themselves. So the materials might get to 1000 degrees centigrade, where just a few centimeters away, it's 150 million degrees centigrade.
And Mira had a question about, let's see, I have a hard time understanding the question, but she said, what about deuterium and tritium make them the easiest isotopes for the fusion reaction? What about those isotopes makes them the easiest for the fusion reaction? Now I got it.
Yep. So in order to get the two isotopes to fuse together, you have to put a certain amount of heat and a certain amount of pressure. And that combination of heat and pressure is easiest for deuterium tritium. So for example, with this magnetic confinement, we only need to get to about 150 million degrees centigrade. There are other isotopes you can use. You can fuse deuterium and deuterium. You can fuse proton and boron. Those require 10 times more, and in the second one, 1000 times more in terms of temperature. So that's why we say it's the easiest. It's not easy though.
They're taking the easy route, Mira. And then, how cold is it? I suspect it was about the cryostat you were talking about.
4 degrees Kelvin. So absolute zero.
Thank you, Kathy.
Yep. Okay, so what you're looking at here is this cryostat base, and it weighs 1,250 metric tons. That's about the same as 208 average size African male elephants. So think about that. That's a very heavy component, and it had to be placed within 5 millimeter tolerances. So very, very tight tolerances. It was actually, there were many people when the machine was being designed that said it couldn't happen. Right? There's not technically a way to do it, but they did it. They were successful. The tokamak itself is, if you think of the shape of the tokamak, there are 9 of these vacuum vessel sectors that are welded together to make that donut shape. And to give you an idea of the size, that's one lying on its side. So why is it so big? Because that's been one of the criticisms. Why do you want it when it's very, very large? It makes it very expensive. When ITER was designed, they chose technologies that had been demonstrated, because what's important for this is the science of understanding how you make those reactions happen and what happens when it's self-heated and that reaction continues. The science isn't how do you design a superconducting magnet. They wanted to make it low risk to be able to do that science. And in fusion, generally speaking, bigger can tend to be easier, not easy, again, easier, because it's very, very challenging. There is a lot that the fusion community needs in order to get to practical, usable fusion energy. And this is not even an exhaustive list, but people of all different backgrounds, engineers, physicists. We need people that understand finance, graphic artists, human relations, all of those sorts of things. So when you're looking for a career, I would say that fusion is an exciting career, and I have certainly enjoyed it in my lifetime. So I know that there have been some questions. I'm happy to answer others. And by the way, behind me, what you see on my background is the tokamak assembly building. And I don't know if you can see my cursor, but sort of above my head, you've got that yellow cover on top of one of 6 modules that makes up the center magnet that is in the tokamak. And the United States is delivering that. That is one of our deliveries, and several others as well. So any other questions I can answer?
Kathy, how many languages do you speak?
So my English is pretty good. I also do speak reasonable Spanish. My German was decent when I was there, and my Russian got pretty good, but they're pretty rusty now. So after about a week, and usually I can do enough to be functional.
Thank you. There was a lot of travel involved, but that should not dissuade you all from these kind of careers, because in most international projects, the common language is English, right, Kathy?
No, that's exactly right. So at the ITER site, for example, English is the common language. They do provide French lessons. And you notice I didn't say French as any of my languages. I need to work on that.
So we have a question. How do you deal with thermal pollution or deal with the heat of the reaction?
So in any of these processes, you do get some waste heat. Now, what I'll tell you is if we could get to the proton and boron from that reaction, you get charged particles, and actually you don't generate the heat. It's not then a conventional fuel cycle. But like anything else, you do need to have an avenue for releasing heat, cooling towers, whatever that happens to be.
And Sarah is asking, what does a normal day look like? It depends in which time in your career, huh?
Yeah. So for me now, when I'm in France, and I go there about every other month, I'll go there again a week from Saturday. I spend time at the site that you're seeing, that you see behind me here, talking with people, trying to solve problems. One of the things that happens in a project like this, and this is anytime you try to build something, and it doesn't have to be a fusion reactor, things don't go quite right. Things may not fit together right. You might find out that what you thought would work didn't work. And so a lot of my day is spent with that problem solving, bringing the right people in to answer these hard questions. But I get to interact. I'll be on phone calls with people from all over the world. That's not unusual. And honestly, the whole travel and that kind of thing, I would say that that's a real plus of working in fusion because it's just a wonderful opportunity.
So Miri is asking, what's the scale of energy produced from fusion versus the energy needed to run the reaction? All supporting parts.
Okay, so we talk about in the fusion world something called gain, and I'm going to do it again from the magnetic confinement perspective, similar though from the inertial confinement. So you've got energy coming in to heat things, and you've got you get reactions that happen and a certain amount of energy out. To just get break even from that particular aspect, you have to be at least 1. For net energies, because we have pumps and we've got things to cool the magnets, you have to get to a ratio of about 10 to 1. So that gives you an idea of how much further we have to go. And in magnetic confinement fusion, we haven't gotten to 1, we've gotten to about 0.7, but ITER will get to 10.
Fantastic. And then when do you think fusion energy can be used on a commercialized scale?
There are many different people discussing that. I was part of a National Academy's panel, National Academy of Engineering's panel to look at that. And one of the things that we said was, we thought it was practical to have what we call a pilot plant, which is the one before a commercial plant in the 2035 to 2040 timeframe. Now, there are some private companies who believe they can do that more quickly. And as a fusion person, I say, gosh, I hope so. As a person who's involved in a project where we're really putting things together, I say, I hope you're right, but I think you can find that perhaps things don't go as smoothly as you want. But it's still a ways away, and it depends on the specific confinement concept. But 2035 to 2040, reasonable?
I'm gonna be too old for that. What do you think is the most interesting thing you worked on?
I really enjoyed doing the modeling liquid metal flow. When you have a magnetic field, liquid metals are conducting, and a magnetic field will induce currents in the liquids, and then those currents interact with the magnetic field, and you get all sorts of interesting shapes. What can happen, for example, is if you've got a bend, depending on the orientation of the magnet field, the forces will actually push the liquid away from the hot part, and that's bad. So you got to figure out how to make sure those things don't happen. So I would say I really, really enjoyed the research that I did. But what I'll also say is living in the Soviet Union for a year is probably my most interesting life experience.
Thank you so much, Kathy.
Hey, I want to get to one more question before we move on. Verena asked something pretty important, at least it speaks to me. She wanted to know, did you have any female role models in your career? If you don't mind answering that.
No. There actually, no, but I've had some, there just haven't been that many women in doing what I do. But I would say that I've had so many important males that have been role models and have really, really helped me and shepherded me along.
Thank you so much, Kathy. We appreciate hearing from you. Super interesting. And it's very inspiring to see, somebody that's done so much, and there's so many opportunities for women to be involved. So this is great. Thank you.
Thank you. And I think I unshared, right? Did I do everything I need to do on my end?
You are fine.
You're good.
Okay, great.
All right, we'll move on to the next speaker. Our second speaker is Derek Mariscal. Derek received a BS in physics from CSU Stanislaus and a PhD in engineering physics from UC San Diego. He is a physicist and part of the Inertial Confinement Fusion, ICF, research team at the National Ignition Facility. He also performs research in short pulse, high intensity laser plasma acceleration, and is working with the cognitive simulation group at Lawrence Livermore to drastically enhance the rate of learning from laser-driven experiments by combining advanced computational techniques such as deep learning with high repetition rate lasers. All right. Welcome, Derek. Thanks for that cool background behind.
Yeah, thank you. Yeah, so this background is actually part of this structure in creating laser beams at the National Ignition Facility. Thank you all for the opportunity to be here. I'm very excited to show you a little bit about what I work on. So hopefully this is all working here. Okay, can we see that?
Yeah, we're good.
Okay, so what you're looking at here is the National Ignition Facility, which was just briefly covered by our previous speaker. So here we have the world's largest and most energetic laser, where we perform fusion experiments. So just a very brief background about me. I grew up in the Sierra Nevadas of California. I went to a community college in Northern California, Butte College in Chico, California, before getting my bachelor's from a small California State University, CSU Stanislaus, in Turlock, California, before going down south to UC San Diego, again, where I got my PhD. And then in 2016, started at Lawrence Livermore National Lab, working as an experimental physicist at the National Ignition Facility with a very large team of very talented scientists. This is just a few of them here, announcing some of our most recent results at the National Ignition Facility, which was also covered, as well as my boss here over on the right, Tammy Ma, who's been a very great inspiration in shepherding me along in my career. So as was already covered, there are basically 3 ways to control a fusion plasma. Of course, there are variations on this and some other concepts, but the big 3 are the natural one, gravitational confinement in the sun, of course, magnetic confinement, and then the flavor of fusion experiments that we perform, which is known as inertial confinement. And why we call it that is because we implode capsules here, this little sphere in the center of this can, and use the inertia of that shell to confine our very high temperature and high density plasma where we ideally create fusion. Okay, so there are many different aspects to this, but typically our research is conducted through experiments on this large facility. But there's also a lot of simulations, machine learning that also supports this. But today, of course, I just want to give you a brief overview of what NIF experiments look like. So there are basically 3 ingredients for what we call laser and direct drive inertial confinement fusion. So first is lasers. We have here a bird's eye view of the National Ignition Facility with the roof taken off. We have 192 laser beams that are all amplified and delivered over to this target chamber, which I'll highlight in a moment. Inside that target chamber, we have our target. And this is basically consisting of 2 main components. One is called the whole ROM, which is about 1 centimeter in scale versus our about 160 meter wide building. And then inside of that, we have a fuel capsule, or that contains our fusion fuel, which is on the scale of about 2 millimeters. So we span a lot of large time and spatial scales. Okay, so again, looking at the building, to put this in perspective, we can put some football fields on and show you that it's about 3 football fields in size. Of course, we're located in the Bay Area in California, so we obligatory have to have Stanford and Cal here, but shout out to Kathy's alma mater, or one of them, UCLA there as well. Okay, so the basic overview is that we have a control room right about here. We have a master oscillator room. This is kind of where the entire process begins, where we seed our laser pulse. Those little laser pulses go out and get amplified by about 1 billion times in energy. And then those are all transported down to this target chamber, which is about 10 meters in diameter, about 30 feet. So it's a very large scale. So now we're looking at the target chamber here, this blue sphere. We can just see the top of it here. A lot of this structure here is the laser beams coming into the chamber. This is where they're finally injected. And then you can see some diagnostics kind of mounted all around. Our next speaker will cover what those actually do and why we need them. So if we now jump inside the target chamber, we can see that we have these very large booms that are coming in. One of them is holding our very tiny target down here in the center. And then we also have some other large booms that are inserting our diagnostics so that we can see what's happening during the experiment and try to learn about the physics of fusion, at least in ICF. Okay, so this is actually a visible light image showing kind of what happens during an experiment. So of course, in the center, we've imploded our capsule. We've created some fusion energy. And we're releasing very energetic particles, X-rays, and lots of things that basically don't like to be heated up are nearby and are getting essentially blasted by what's just happened in the center. So to look at the target in a little more detail, so this is kind of the scale of what we call this hole ROM. The laser beams are going to enter through two small holes that are on the top and the bottom and heat the inside of this can. And that's going to create a hot bath of X-rays, and those are essentially going to cause the capsule to react by imploding and rocketing inwards. So here's the scale of a capsule. We can see it in relation to the size of a dime. It's about 2 millimeters, as I said. This is filled with our fusion fuel. And the challenge is to spherically and symmetrically compress this down by a factor of about 35, down to less than the size of a human hair on the scale of 50 to 100 microns. So this is analogous to essentially trying to compress a basketball down to about the size of a pea. So now we're going to actually run through a video and show exactly what this whole process of firing a NIF shot and performing a fusion experiment looks like. So hopefully this isn't too loud for you and you can still hear me. We're going to enter the building and go into the NIF control room where various technicians are getting set up for the shot and defining all the parameters that we want to input, as well as one of our scientists that's ready to conduct that. So the process starts, as I said, in the master oscillator room. We're going to move over there, and here we create the initial or seed laser pulse. And that laser pulse is going to get sent out of this master oscillator room to the amplifier chains. So it's going to be split up into 192 seed pulses, and as light bounces around, it's gaining more and more energy. It's going to move into the main amplifiers. Now this laser pulse is about 20 nanoseconds long, and that's about how far light travels. Light travels in about 20 feet in that amount of time, and so the laser pulse is effectively about 20 feet long, and it's bouncing through back and forth to gain more energy, and then it's being transported towards that target chamber. Now the final thing that's going to happen here is that we're going to change the color of our laser light from red to blue, and then we are pointing and focusing that down into that hole ROM target. So now as we go in closer here, we can see that the laser beams are hitting the inside of that can and creating those X-rays, and this spherical capsule is now going to rocket inward and hopefully produce fusion. And then we're also going to study that through our diagnostics, where we can see some pictures coming out, and then our scientists can take that back compared to simulations, and we can basically study the physics of ICF. So That is our overview of what a typical NIF experiment looks like and what's actually happening under the hood, so to speak. Okay, so what has happened is that it's taken us over a decade since we first brought NIF online to make progress and get to those exciting results that Kathy mentioned. So by 2021, our experiments had produced about 70% of the input energy in terms of what the laser input to the target. Basically, the way that happened is that we essentially had to go through a learning process of how to control the symmetry and mitigate some instabilities that were basically preventing us from getting very close. But we finally reached this burning plasma regime, and we're very excited about that. Of course, the next steps are, can we improve that even further? But also, can we do this repeatedly? And as was said, just in December of last year, so just a few months ago, the experiments produced 150% of the input laser energy, which is what we call ignition. So this is an extremely exciting result. But this wouldn't have happened without a myriad of careers. Kathy had a very long list. I think that, as she said, that's still not even exhaustive enough, because there are many, many supporting careers around our fusion research at the NIF. And that comes, just to name a few here, from lasers and optical technologies to build a facility like NIF, the simulations and machine learning that support the physics in the background, building very exquisite targets. These have to be very precise, and of course they're at very small spatial scales, so they're very difficult to build. And most importantly, we have to figure out how to learn from our experiments, and the way that we do that is through diagnostics. They're the only way that we can see what's actually happening on these ultra fast and ultra small spatial scales. And luckily for you, our next speaker is going to show you what that looks like. So that's it for me. Thank you for your time and attention. I'm happy to answer any questions.
That was great, Derek. Thank you so much. Go ahead and put your questions in the chat. I'm not seeing any just yet, but we'll give you all a few seconds to.
Derek, I have a question. Sometimes students think that going to community college is the bad choice, and you are an example that it's not.
No, from my background, I wasn't really sure exactly what I wanted to do in my career path. And I knew that I could basically get about half of my undergrad completed without making that choice, and at very low cost. So that was the route that I decided to go. And also with the state university, it actually worked out to be a very good situation. I graduated at our physics class was 8 people, about half women. So we had a lot of one-on-one, time and attention from our professors.
That's fantastic. And it's something that sometimes, students hear, you need to go to a Ivy League kind of school to be successful. And we try to tell them that if you don't know what you want to do, expose yourself as much as you can to other fields until you find your passion. And then, put all your, how do you call it? All your balls in one basket then. But until then, just keep exploring. And I think, Gauri, there are some questions. Would you like to ask those questions?
Sure. Mira wants to know, could you explain a little bit more about how inertial confinement works?
Yeah, so essentially by compressing that sphere full of our deuterium tritium fuel, we're going to necessarily squeeze all the atoms together, and they don't necessarily want to be that close to each other. So that's going to create basically collisions and heat, and increase the temperature. And as Kathy explained, once you get to high enough temperature, you'll actually be able to get those atoms to fuse. Does that help?
I think that's a great start. Thank you. Mira, you can always follow up if you'd like, if you have more specific questions. Verena asked, what does your day-to-day look like?
So for me, I actually spend about 50% of my time on fusion research and about 50% on some other exciting projects. So day to day, it's mostly meeting up with various teams. We have different goals as far as studying different aspects of the fusion science. And I also lead some teams on the machine learning applications, the high repetition rate lasers. For NIF experiments, they're very different than the other type of experimental work that I do, because for NIF, we have many people that are supporting those experiments, and those basically get executed based on months and months of planning. For the other side, occasionally I'm out traveling to actually do experiments at sort of university scale facilities. And then on top of that, probably half of my day is actually analyzing data or coming up with new ways to analyze data. But yeah, about 50% meeting with those various projects, 50% on data analysis, and also travel, to conferences, things like that. So
Sounds
see.
good. So, yeah, sounds like you have your hands in a lot of different things. That's pretty exciting. Maya wants to know, are there multiple hold rounds at NIF, or is there just one?
Yeah, so we actually completely destroy the target every time we take a shot. And so there are many hole ramps basically that are constantly being built. Yes, so there are a lot of them. We shoot one at a time.
Sarah is asking, what part of the lab do you work in?
So I actually work in as far as organizational structure within the National Ignition Facility.
Okay. Anna's question is, who can do experiments at NIF, and who chooses which ones are shot?
That's a good question. So I think I might be off a little bit on this, but about 90% of our experiments are kind of laid out for various goals in science that we have at the lab. A lot of them are in support of ICF. There are also some other interesting physics problems that you can study with the laser as powerful as the NIF. For the most part, those are conducted internally. We also have other national labs that come to conduct experiments, such as Los Alamos, which you'll hear from one of those scientists next. And then a small portion of our shots that we conduct in a year are actually dedicated to what we call discovery science. So academic institutions or even international institutions can propose shots through that. And those are basically geared towards like basic science. In fact, I'm involved in plenty of those as well.
Sounds good. So Mira does have a follow-up. She says, I think it was mentioned earlier that for magnetic confinement, that keeps the nearby materials from melting. How about inertial confinement? Does that also use this, or is there a different mechanism? And she says, sorry, she might have missed it, but what is your Zoom background? So maybe you can start with that and then tell us more about how the confinement works.
Okay, so for the confinement, it is actually the mass of the shell that's coming in that's basically pushing everything in. And then for a fraction of a billionth of a second, there's enough inertia in that shell to keep things confined. And that's where we're having our fusion reactions. We don't at present have to necessarily worry about what's getting heated up. The National Ignition Facility is not actually designed to, say, generate energy for the grid or anything like that. It's actually just a scientific research facility that's trying to demonstrate the physics of this and demonstrate the possibilities. But commercial operations will have to look into how to actually engineer a system that could put energy on the grid. As you may have seen in one of the pictures, the things that we do put near those implosions, which eventually explode, those have to be protected, but we do that with what we call debris shields. So those basically get also damaged, but without damaging our high precision instruments that are behind those. The background is part of the support structure for part of the laser at the NIF.
Awesome, thank you. Shani actually asked a question that's been on my mind too. She said, thank you, that was a really cool video. Congrats on the recent success. What was the breakthrough that led to so much gain?
So that is an interesting part, but it's basically the story that I told you about. It's taken decades for us to really understand all of the physics inside this very complex target and interaction. So more or less, a lot of it was actually just taking sort of the best aspects from various different designs and putting those together, and then basically modeling and understanding just how impactful some of our small imperfections in our targets were going to be. So getting better targets and realizing that actually some of those small imperfections can actually have huge degradations, and essentially put in sort of a cooling rod into our fusion reaction. So getting rid of those and designing so that we're not as susceptible to those is kind of the major recent breakthrough.
Well, that was awesome. Well, thank you so much. I certainly learned a lot. Before we move on to our next speaker, I want to say thanks to all of the students that have your webcams on. It really is nice for us to be able to see you and look at your reactions. Sometimes we have these surprise reactions in our face too, and so it's nice to see you guys reacting as well. I'm going to move on to our third and last speaker today. It's Dr. Verena Geppert-Kleinrath, and Verena is actually one of the scientists in my own organization, so I'm very proud to introduce Verena to you today. Verena is an international leader in the area of nuclear imaging for inertial confinement fusion that you just heard about. She and her team at Los Alamos National Lab have successfully developed 3D neutron and gamma imaging and radiography diagnostics for the NIF, the Omega Laser Facility, and the Nevada National Security Site. Her nuclear imaging diagnostics have delivered key performance metrics for the recent high-yield ICF implosions on NIF that we also just talked about. She also leads the team that performed ICF ion temperature imaging for the very first time in 2021. Dr. Geppert-Kleinrath has authored over 50 publications in internationally circulated academic journals with over 800 citations. She holds a PhD in nuclear physics from Vienna University of Technology in Austria. She's also a mom to 2 young children and serves as a ski patroller on her home mountain in Los Alamos. Other than her family and skiing, she loves cycling, hiking, and fly fishing. And welcome, Verena. Thank you so much for being here, and take it away.
Great. Can you hear me and see my slides?
Yes.
Okay, thank you. Thank you so much, Gauri, for the kind introduction. And thank you to the organizers today. This is a really cool event. And also thank you to the previous 2 speakers. Those talks were really cool. I learned a lot as well. And most of all, though, thank you to the students that are here. I'm so happy to be here and share my science. And I'm really excited that you guys are excited for science on a Saturday. So thank you for that. We've heard a lot about fusion in general, and then we've heard from Derek about how the National Ignition Facility works. My perspective is of someone who works for that facility, but remotely, from Los Alamos National Lab. and I do diagnostics. So my team will tell scientists like Derek how an experiment worked and whether it worked, and give him some feedback so that he can go back and make some improvements for the next one. All right, let's see, there we go. Before I jump into the work, a little bit about myself and why I like my job. The first answer to this is, I enjoy working as a scientist at a national lab because I really believe in government-funded research. I think that it affords us the opportunity to solve challenges that are really, really big for the nation and also humanity as a whole. And I think fusion is a very good example for this. It requires these, large facilities that you've heard about now, and lots of different people to work together. So I think that's the best way for me to apply myself, and I really enjoy that. I also love New Mexico. I saw in the poll that there was at least one person from New Mexico. If you're not from here, please come visit. It's really cool. There's amazing outdoors, and there's a rich cultural history, and it's all on our doorstep from the laboratory. This picture is of me fly fishing in the Valles Caldera National Preserve. That's just 15 minutes from the lab. And that shows that there's some good work-life balance to be had here as well. I'm a PhD nucleophysicist. That means lots of schooling, like the previous speakers have talked about a little bit as well. I obtained my last degree on my 30th birthday. So it took me a very long time to get my education. Some of it was very stressful and very hard, but I would say I would do it again because it's been extremely rewarding and very, very interesting. I'm now a team leader at LANL. That means that I have a small team of about 5 to 10 people, depending on how our staffing is, to lead science experiments. I work with physicists like myself, but I also work with engineers. I work with computer scientists. I work with technologists and that don't have a graduate degree. And I also work with students at all levels. I have worked with students in high school and post-high school, undergrad, graduate, and then a big driver of our scientific workforce are postdocs. Those are people that have recently obtained a PhD and are still getting a little bit of training, and they're just starting their career at the National Lab. I'm also a mom. I have a 6-month-old daughter and a 3-year-old son. I can definitely recommend that. That's been probably the best part of my life so far. So that definitely trumps science, but also we're able to make it work to have, both children in scientific careers. Both my husband and I are scientists. Both of us work at NIF. And this level of education affords us some level of flexibility that makes it possible for us to have a family. I also am an immigrant. I'm originally from Austria. I knew relatively young that I wanted to be a nuclear physicist sometime late in high school because I read about the work that nuclear physicists were doing at the International Atomic Energy Agency, which is based in Vienna. It's a United Nations organization that promotes peaceful use of nuclear power and nuclear research. It was in the news when I was in high school because of the dawn of the invasion of Iraq and the discussion on whether that country had nuclear weapons or not. And so I knew at that time that I wanted to do some sort of work that could make that sort of impact and, be important in the scale of, our humanity. And so that's why I now enjoy working at a very international organization. I was able to do my master's thesis research with the IAEA, but I did all my experiments in Karlsruhe, Germany for the European Commission. So a touch point with Kathy's work there. And then there's another one. I was able to present my research at a conference in South Africa where I met Kathy McCarthy for the first time, and we clicked and connected. I instantly saw her as a role model. As you have heard her say, there have not been that many women in nuclear physics or nuclear engineering yet. So I sought her out at that conference. And she already held a leadership position at Idaho National Lab, and she got me in touch with people that ultimately helped me find a PhD project that I could work on here in the United States. So I came to the US in 2011, and then I moved to Los Alamos National Lab in 2012. And the group that I started in, I did nuclear physics, fundamental nuclear fission physics, was a group that Anna Lobet also worked in. So I met her a long time ago as well. And she's also a role model to me. And I would say in general, I think having some female role models in my life have been a better spark for my career than anything else. I think even more important than technical mentors. And what you can see from this picture, I'm also an outdoor enthusiast, if you haven't, caught on to that yet. So living here in Los Alamos is a great way of combining that passion with my passion for science. All right, let's jump into the work. There we go, this direction. So brief recap, we've learned this from Derek now. He's explained this very well. How does inertial confinement fusion work? We have these very small capsules that you see at the top left here. We shoot lasers at a hole round. All the hole round does is convert these lasers to an X-ray bath. And then we compress those capsules and heat them. And then fusion reactions happen if we're hot enough and have high enough pressure. And these hydrogen isotopes will fuse, and there will be some products on the other end and some energy. And the reason we have some energy there is because the products, or the sum of these parts, is actually lighter than the individual elements that we started with. So according to Einstein, E is mc squared, we will have now created some sort of energy. One way energy is created there is the kinetic energy, or the speed of these neutrons. And as you can see from this picture, as neutrons are directly created in fusion reactions, so they're a great way to diagnose what's going on in your experiments. If you can measure the neutrons, you can know what's going on. And at the bottom here is just one more time, a reminder, the laser drive compresses. What's happening then is called ablation or rocket drive. We're burning off the shell that we had that contained that fuel, and that drives that capsule inwards. We now have very strong compression, like the basketball to a pea. And we also have shock waves that go back and forth. It's an implosion. And those then all create those really hot and dense conditions that we need for fusion. So my team provides a picture at what's called stagnation, which is the time, when this is the most compressed and the most fusion reactions happen. Our diagnostic is time integrated, but we see mostly when this is at its peak, this reaction. And what we would have at that time is we would have something that's about 100 micron, that's about a hair or two, 1/10 of a millimeter. We would have some fuel in the center that's currently burning, where fusion reactions are happening. We would have some fuel around it that has not burned yet. If we burn all of this up, that's the goal. That's we will get energy gain. And then we might have some remnants of this shell that we talked about, the capsule that the fuel was contained in. And we now look at these neutrons produced in the fusion reaction. We measure them directly, the ones that come out. They have just one energy. They're very characteristic. They're fast neutrons. Some of them bump into something else, like the cold fuel, on their way. So they lose some of their energy. What happens when neutrons lose energy, they become slower. So they will take a longer time to get to our detector. So by timing our detectors, we can choose which ones we look at. So we can take a picture of that burning hotspot, or we can take a picture of the fuel that's not burning yet. Or the last thing that we do is we also look at neutrons that bump into a remaining shell, if there is one. And if it has some sort of carbon, usually they're glass or plastic, so then it does have carbon. And there is a specific nuclear reaction where those neutrons will bump into that shell and produce gamma radiation. That's another type of radiation that we can measure. It moves with the speed of light. So once again, with timing at our detectors, we can choose only this radiation to take a picture of. So then we can tell you whether there was a shell present, and if so, where were these remnants of the shell. And the way our imaging diagnostics is the principle of a pinhole camera. So a camera obscura, I don't know if you've seen one maybe in school. The simplest way of doing this is you have a big cardboard box and you make a tiny hole in it. And when you then look at the back side of that box on the inside, you will see an image of the scene on the outside. That's how a pinhole camera works. And that's exactly what we do here. We have an aperture that's very close to that source, about 30 centimeters, and then a detector about 30 meters away. The reason we do that is first we get magnification, because in a pinhole camera, when you move that hole closer to what you want to image, and the image that you project is far away, that image will be much larger than your source. And we also do that because when we're so far away, we can do that distinction in timing between fast neutrons and slow neutrons, because they will take enough time to get there so that we can capture an image at that time. And then our recording system is just like some sort of camera system. It's a specialized lens and intensifier and camera setup. And our apertures are not just a hole in cardboard, because radiation interacts with these apertures a little different than standard light. So you need a very dense material, something like gold, something like tungsten, and it needs to be very thick. So ours are about 20 centimeters long. And these holes in these apertures are very, very small. They're just a few microns. So even a tenth of a human hair, very small. There are also many of them, so we get more statistics and we can point them easier. And they also have odd shapes, which makes it a little bit more complicated. We don't get an image that looks exactly like the source. We have to do some computing to get the right image out. And the scales of this work out to watching a 24-inch TV through a telescope from 100 miles away. So you can imagine that it's really, really hard to align this properly, to not miss the TV. And we have to do this every single shot. Every time we do a shot, which is about once, 2, 3 times a week, we have to insert that aperture again into that target chamber and hit it right so that we can actually see the source. We have 3 of these big imaging systems right now, 3 lines of sight that are almost orthogonal. And we do something called tomography techniques. We take 3 pictures, one from each line. And then with tomography, we produce a 3D object, a 3D reconstruction. And that's very similar to when you go to the doctor and you have something called an X-ray CT. That's just short for computer tomography. They put you in a tube, they take many, many thousands of pictures and then produce a 3D reconstruction of whatever part of your body they have imaged for your doctor. This is very similar. It's just that our individual lines of sight are multi-million-dollar projects, so we only get 3. That makes that a little bit more complicated. And then on the right here, you see one of these 3D reconstructions. This is for the big shot now in December when we achieved fusion gains. So we got 1.5 times more energy out than we put in with the laser in this experiment. And this looks relatively simple. This is just a ball of fusion. That's because it worked. As Derek has already said, we're squeezing a basketball to a P. The way this physics works, this plasma physics can be described like squeezing a water balloon. We call this hydrodynamics. Works a little bit like squeezing a water balloon with your fingers down to a very small size. And now you can imagine that the water balloon is trying to squirt out everywhere between your fingers. And if there was a little, that balloon was a little damaged at one point, like a little bubble might form and, lots of complications like that. So typically our images don't look as boring. They kind of tell us what went wrong. So we'd see a piece of the ablator shell has jetted into the center. It's cold in the center now. That's why it didn't work. That's kind of the type of images we get. In this case, it worked perfectly, and we just got a round ball that's hot in the center. All right, and then I also want to show you, skip the slide, sorry about that. a different project. We have these established diagnostics on the National Ignition Facility that we work on, but we're also currently working and always really working on developing new diagnostics. And here's an example of a project that I led recently where we want to do ion temperature imaging. So when this is done, we want to tell people like Derek at NIF that his implosion was really cold on the top and very warm on the bottom, and then we can figure out what to do. Because ion temperature is one of the key plasma variables to understand inertial confinement fusion. So that would really help us compare the simulations a lot better if we could say, you know, what the temperature was in the implosion. And the way we do this is this plot on the left here shows 3 different temperatures of this plasma and their neutron distributions. I told you that usually the neutrons come out at just one energy. But what happens when it's very hot, there's a lot of energy in that plasma and they move a lot. Everything moves a lot. There's thermal energy, thermal broadening is what it's called. And that just means these things bump into each other a lot. And so there's some that are now slower and some that are faster. And so we will have in our burning hot spot, the hotter it is, the more of a distribution of energies. And we had already talked about that distribution of energies can be measured with a distribution in time when you have a detector very far away, because now these very low energetic neutrons will take a much longer time to get to our detector. So that's the principle we're using here. And then we're doing something called 1D imaging. It's not very intuitive because, you know, usually our images are not 1D. But we get spatial information along one axis. So we have an aperture here that's not a hole, but a slit. So we only get spatial information top to bottom. So then we have a detector that is pixelated in that direction. And then we have something at the end that's called a street camera. What a street camera is imagine a film camera where someone's pulling the film out while you're taking the picture. So now we're smearing one component in time while the other one still contains our spatial information of our image. And so that's what we're doing here to take a 1D picture, basically. And here it is. Here on the left, that's the first time anyone has ever taken an ion temperature image in inertial confinement fusion. I hope it looks as exciting to you as it does to me. So let me tell you what you're seeing here. From the top and the bottom is that slit aperture. So that squeezes this image here a little bit. We have no intensity at the top and the bottom, and it's very hot in the middle. So that encodes the spatial information that we have to reconstruct. And then in this direction, we have time, which corresponds to the energy of these neutrons. So when you see an area where the distribution is very broad, where you have like a lot of different energies, that means it's very hot there. So that's what this image tells us. The reason I wanted to show you this project is not just because I think it's cool physics, but also because this project was led by some of my team members, a postdoc, and also 3 students. So here's a picture of 2 of my undergraduate students that were instrumental in this experiment, and also another PhD student that will write his PhD thesis about this particular project. And one of these 2 undergrads is now a graduate student and just got a National Science Foundation fellowship and will lead a new project bringing this diagnostic to 2D and to the National Ignition Facility for his PhD. So I just want to emphasize that every level of team member in my team makes a very meaningful contribution to science. And so at any level, you can start doing science, and it doesn't need a special person. It doesn't need special talent. It doesn't need special intelligence. It just needs someone who's interested, who wants to work in this field and wants to learn. That's all it needs. And I also want to leave you with the slogan of it's a great time to work in fusion. There's been a lot of exciting developments recently, as my 2 previous speakers emphasized as well. This is another Lanel diagnostic that you see here. That's the one my husband works on. It's a timing diagnostic, and that's in a Star Trek movie. So I think Kathy had that image as well. Yeah, if you're ever in Los Alamos, or if you have any questions, about fusion, about my career, about myself, please don't hesitate to reach out. Or if you want to work for us, Verena@lanel.gov. Thank you.
Thanks so much, Verena. That was excellent. I'm going to get you started off on the questions. Anna, actually, since you mentioned you've got a team with a lot of undergrads, etc. Anna is asking, can you explain how undergraduates interact with the NNSA labs? Because people get degrees at universities, so where do DOE and our national labs fit in?
Yeah, the way I found my undergraduate students is I actually found them as high school students. They came through a program called the Los Alamos Scholarship Foundation. It's a very nominal, small contribution, I think, to their college tuition early on, and you can apply for this when you're still in high school. And then these students get matched with mentors, or mentors have CVs available to them on our webpage at LANL for summer internships. So these are all students that wanted to do summer internships. That's a very big program at all of the national labs. I think you can go to their websites, to their jobs web pages. I think all of us are always looking for summer interns. Thousands of people come to Los Alamos in the summer to work here. And that's a good way. These are, of course, paid internships. So this is a good way to also, pad your checkbook for the expensive college experience. And my experience has been with my own students that you kind of find someone that works in research that can help you navigate this really challenging world of, high tuition colleges. Do you switch to a better school after community college, grad school admissions? Working at a national lab, you're not just learning science, but you have a lot of people around you that went through a similar career path that you might be aspiring to. So there's always someone to help with like grad school applications or, give advice on that sort of thing. So that's been, the undergrad interacting with the national labs. I think the biggest program is the summer internships.
Yeah, and I want to add to what Verena said. You don't even have to come on site. After COVID, we're doing a lot of virtual internships as well, where you can maybe come visit for a week, but then the other 7 to 9 weeks, whatever you're working from your, wherever home is. So we're a lot more flexible these days, and I just wanted to throw that out. So Verena, maybe I'll ask you a question. What is one thing you wish you had known when you were in high school? What did you think being a scientist was? Because I know you said you always wanted to be a scientist. And so what did you think that was? And what is the one thing you wish you knew?
The one thing I wish I knew that is still true, I wish I knew this today because I'm telling myself, but sometimes I don't believe it, is there is an Austrian saying, so I'm going to try to not botch the translation too much, but it's like everybody boils with water, which all it says is, everyone's just trying their best and there is no special genius level required to be a scientist. Science is not this old man that sits in a room and comes up with a brilliant idea. Science today is these large facilities that both these speakers have shown today. It's teamwork, it's people of all walks of life. It should reflect our society, right? I want to work with people that look like me and people that don't look like me. And there can be different professions in the sciences that all work together. You don't have to have a PhD, but of course it doesn't hurt. But I think I just wish I had known that science can be accessible to a normal person, right? I think we need to be, it's really nice to have role models, and I have admired many women in my career, but I think we need to be very careful about putting people on a pedestal. Everyone's just trying to get through their day and make it work, So I wish I had known that I can just be interested and do it and not have to have some sort of talent.
That's a great response. And actually that kind of segues nicely into Anna's question. I'll let you start first, Verena. Anna, talked about, can you talk about your take on imposter syndrome? And I'll tell you, this is very relatable for me because I pinch myself, every now and then wondering, am I really working at a national lab? And so what do you think, Verena?
I think I'm just now slowly learning, right, that I shouldn't have imposter syndrome, that I belong here and I do meaningful work. So I have to tell myself that every day. I think there's a thing in there about confidence, right? When young students, when you see us, the people here on this panel now, you will think, oh, she's doing amazing work. She's so confident. It's not true. It's you're always you, and you're trying your best. You're uncertain. You're nervous. I'd say today is one of the days where I've been the most nervous about giving a talk, because I think you guys are the most important audience that we can have, the next generation. It's much more important than when I give a talk at a technical conference. But if you see confidence in a leader, it's usually because they have been in that situation 100 times. I'm still nervous in a new situation. It's just that when I interact with my undergraduates, something that I've done, over years, mentor people, I might seem more confident just because I have practice. But once again, there's no special, super confident leader that has it all, I think. It's just people have been in situations before and they've learned from them, and now they're confident in that particular situation.
That's a great response. Thanks, Verena. Derek, how about you?
Yeah, I don't know how much I have to add to that, but that it's a very common feeling. Being even through your studies, because you're going to inevitably be learning from someone that knows much more than you. And so there's always these new environments where you think, oh, you might build up your confidence and then you get to the new environment and then you think, oh, like I don't belong here. And I should have mentioned earlier too, but my wife is also a scientist that works on the NIF, and we commonly talk about this sort of thing. We both go through periods of still to this day feeling that imposter syndrome. But you will get, as Verena very nicely said, you will get more comfortable with it. It's new situations, and you just have to kind of develop that experience, and you'll get comfortable. But it is difficult, and by no means as much as it might appear, we all experience it.
Sounds good. Kathy, do you have anything to add to that? And Verena, can I ask if you wouldn't mind stop sharing your screen?
So yeah, I absolutely agree with what the previous speakers have said. And I can tell you, every time I've gone into a new job, when I walked on the campus at the Canadian Nuclear Laboratories and I was going to be in charge of everything, I thought, oh my God, what have I gotten myself into? Because why would they let me do this? So it's not something, even when you have many, many years of experience, because I am that old, but you still wonder. And I think what's a little bit different for me now is within a day of when I was up there, I thought, oh yeah, I can do this. I really do have something to bring. So I think you kind of start to get over it a little more quickly. But one of the things I'll tell you along this, and here's one of the things, if you look at differences between men and women, generally speaking, right? Not always 100% true, but generally speaking, when you look at a job ad, a woman will look at a job ad that has 20 things that they have to be good at. And if they're not good at all 20 of them, they don't apply. Men are much better about it. Oh my gosh, look, I can do number one, so I can do all of it. And so that's something that, generally speaking, women need to be a little bit better about that. Don't think that you have to do every single one of those things. And from the employer's perspective, one of the things that we're trying to do is make sure the list of required things are really required, right? Some are nice to have and some are required, but you can learn many of the things that people need you to know to do a job.
Yep, very well said. Thank you so much. I think we're just about out of time, and I want to thank all three of our speakers for a very engaging session today, and thank you to all your students. Yes, let's have some applause for the speakers, please. And thank you to all the students. So let's have some applause for our students as well. It's so heartening to see so many of you interested in science, and I can't remember who said, taking part of your Saturday to be involved in a discussion about science. This is wonderful. Wishing you all success in your journeys, and please don't hesitate to reach out to people, find your own mentors and find your own journey, and we're all here to support you. Our next Sage Live will be on April 22nd, and the topic is artificial intelligence and astrophysics. You've got, the links on how you can follow us on social media and subscribe to our channels, etc. Thank you all so much. Have a wonderful rest of your weekend, and it's been a pleasure. Thank you.